Well, welcome to this next tutorial, and today we're going to be looking at shift registers, in particular the CD4021B. So, what's a shift register? Well, this is my sort of breadboard today, and this all comes down to an issue with a traditional board. Now, we know that the board's got a number of digital pins, some analog pins, but the project that I wanted to work on is part of a model railway thing, and I needed a lot of buttons connected. And when I say a lot of buttons, I mean a lot of buttons. And let's be honest, the number of digital pins wasn't going to make it. Now, the usual alternative is we just go and buy ourselves a Mega, and now we've got, what, 53 pins. Problem. That wasn't going to make it for this project either. I needed to have a system that would use at least 100 pins. For anybody who's ever seen a great big model railway control panel, the old analog ones, 100 switches and buttons was quite normal. The other thing is that the project I'm doing is going to use ESP now, and boards that have ESP now are pretty small. So I needed some extra pins, and that's where the shift register comes in. So this is my sort of breadboard mock-up. Sorry, it's a bit of a mess. I'm running out of wires because they're all in something else. And what we see on here are the two shift register chips. Now, this is a photo of the chip that I took a little bit earlier. As you can see, it's just a 16-pin chip, but this 16-pin chip connects to the Arduino using 3 Arduino pins, but in turn it has 8 inputs that I can use as digital inputs into this chip that will then pass the data back to the Arduino. So using one of these chips, I can have 8 buttons where I would usually only be able to fit 3. However, it gets better, because you can daisy chain these chips. Now, in this example I've done here, you can see the first chip and then daisy chaining over onto the second chip, but at the same time I still only have 3 wires to the Arduino. So now at this point, what I've done to save the drawing of this, because it got so complicated, where you've got these pull down resistors, they're 10k resistors on this one. For each one of these you can add a button like this one. So these are pull downs. So here we've got a switch that's connected obviously to the 5 volts, and I can then repeat this for each one of these resistors, and so by the end of it I would now have 16 buttons. However, I can now stick another chip and another chip and another chip, and for each chip I can just keep adding 8 buttons. Now, because these don't have an addressing system, you can realistically add as many as you wanted. I'm sure there will be some limitations on speed eventually, but I very much doubt I'm going to get that far. My project, I need to have a minimum of 100 buttons allowable, and even with a basic Uno it's going to manage that with no problems at all. Just one little aside on this circuit, I've obviously using 2 of these with the Arduino. If you were starting to use a lot more of these, what you would do is disconnect the 5 volts from the Arduino and supply the 5 volts from a separate power supply, because you can't keep adding endless resistors into a system that are going to draw their power off the Uno. An Uno is not a power station. If you're going to have a lot of these things, it will definitely need a separate power supply, and all you would do is just make sure that you connect the 2 grounds so that everything has a common ground. So before we start looking at the code, let's just start getting an idea of how this works. So if we look at a conventional Uno, if we wanted a number of buttons, we would connect them all to the various pins using a pull-up or pull-down resistor, and we would use digital to read to find out if those pins are high or low. Obviously, as we've said, we're limited by the number of pins available on the Uno. With our shift register, as we'll see in the code in a bit, we have three pins. One is what we call the latch pin, one is a data pin, and one is a clock pin. And there are basically 8 connections, 0 to 7, that can connect to your buttons, as you see in the wiring diagram that I showed you earlier. And of course, each of these buttons can be on or off. And just like our digital read, the shift register is reading the state of each of these pins. So if we say that pin 0 is off, pin 1, we've pressed the button, so it's high, we've got a 1, low, 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 high, low, low. So the shift register has 8 pins. Guess what? In a byte, it's made up of 8 bits. So what happens is what's called the latch pin, if you like, unlocks the unit and says, okay, we want some information. It then sends a byte of data, and that byte of data is a representation of the pins that are being pressed. The clock pin then does some stuff to get it ready for the next byte, if that is applicable. Obviously, if there's only one shift register, we don't have to really worry so much about that. I'm not going to go into the technical details of that. You just need to accept that the latch pin basically opens the lock. We then start transmitting data, and the clock pin sort of deals with that transmission. Now, when we add more shift registers, this is where the magic really starts to happen. So as we've said before, the latch pin unlocks the system. We send the first byte of data, the clock pin does some stuff, and then if we call the function again, we leave the latch pin open, so we've unlocked the door, we call the function again, and this time it sends the next bit of information. We call the function again, it will send the next piece of information. If we keep calling the function to read these shift registers, it's a bit like pulling information down a drain pipe. One piece after another is coming out of that drain pipe for as many shift registers as we've got. And then of course, once that's all over, we lock the system again. So that's basically how all this is going to work, and we'll now start to look at the code. Now at this point, I thought this was going to be a dead easy job, because there is a page on the sort of Arduino site that gives all the information on how to build the circuits, sample code. There's absolutely everything. So this isn't going to take many minutes to finish the job. Unfortunately, when I built all of this, it didn't work. Now, usually when people blame the code or whatever, most of the problems I've ever found when coding stuff has always been down to wiring issues. So I stripped the board down and I went back to the diagram and I worked through it step by step, and I thought, okay, what's going on here? Because I've done this in the past. I've used these before. It was just I was refreshing my memory because it's been a good couple of years since I last used them. So I thought, go back to some source material, get it all right. Went through all this again. It didn't work. I'm running this code that's down here and it's failing. And I was getting some really odd results. I was getting certain values from certain pins, but in my view they were wrong, and register 0 I was never getting a value from. So once again, you sort of scratch your head and you think, okay, I've done something wrong here, maybe the chip stuff. So I changed the chip again, and then I started to think maybe there's more to this than meets the eye. So this is the code running. As you can see in the serial monitor, I've got button 0 and button 6 being pressed, and buttons 2 and button 4 being pressed. Now if I go back to my board here, if you watch that serial monitor, let's just try and blow it up a bit so you can see better, he says. Let's just pull the wire out and you'll see this is what I'm using for a switch. If I pull this out, all of a sudden now the one board has only got one button being pressed. Push it back in and we're back to two buttons being pressed. And obviously I can do the same with the other board. If I just figure out which wire it is, yep, it's that one there. If I pull that one out, you can see again I lose. I'm going to pull a second one out so we can see we're now down to one button being pressed on each of the chips. So let's have a look at the code and see how this is working. Now, just before we go into the code, one thing I'd just like to say my thanks to someone called Runaway Pancake. I searched online for people having the same problem, and eventually I came across a thread on an Arduino forum where someone who went by the name of Runaway Pancake had solved the problem for someone else. Now, he'd written some code that made everything work. It wasn't quite suitable for what I wanted to do, but I'm very thankful to him because it gave me the direction in which I needed to go. And the first thing it meant was not using the standard shift in that's a built-in Arduino function. Now, I'm not sure with the error that I'm having whether it's a particular batch of chips, a particular manufacturer, or as someone said, that possibly a fault with the shift in function. I do find that a little bit hard to believe after all this time, but I'm open-minded. But if you've got a problem with these CD4021B chips, there is a way round it. So let's have a look at the code. Now, because I wanted to build a system that could use multiple chips, I really wanted something that was easy to configure, and this is a little cheat that I do at the top. So I'm going to store all the data in an array. Now, this is, if you like, the data coming off these. So I want the, if you can see here, I've got a definition here, num CD4021 chips, otherwise the number of chips that I'm using, and that is then placed in this array. Now that means that if I want to configure the array and all the rest of the code, if I suddenly want to put 10 chips in this code, all I've got to do is change that value to 10 and it instantly works. So when I say I wanted a very configurable system, that's what it's about. As you can see above, there's a little demo of which pins are connected to where. Again, thanks to Runaway Pancake for that one. So we have 3 pins that I've got connected: the latch pin, the clock pin, and the data pin, as we see on our diagram here. I don't like delay, and I don't like delay even in my demo code, because what happens then is people then put that code into another project and the delay blocks the code. So we're going to use current millis and a delay that's set by millis and a delay timer that is 2 seconds. Obviously I've started the serial monitor. I've then marked the latch pin as the clock pin. They are outputs, so they are sending information to the system. They are telling things when to open the lock, when to start doing various things, whereas the data pin here is an input, because that is receiving the data from the chip. Now, in the main loop, current millis just takes the time in milliseconds. Current millis minus the delay millis. If it's greater or equal to the delay time, that means every 2 seconds it's going to take a reading. Obviously, in reality, you would want this, if you're going to use it as a debouncer, which you could also use it for, you would want realistically to be checking the button about every 0.2 to 0.3, 0.4 of a second, depending how sensitive you want it. Again, all you would do is just change the value up here. I've slowed it down because otherwise the numbers are whizzing by so fast I can't see anything. Then, as always with this sort of code, delay millis now equals the current millis, so the system is now set, so in another 2 seconds in my case it's going to do its stuff again. So what does it do in the main loop? Well, The main loop is tiny. So I call two functions. The first function is latch 4021 and it sends the value of the latch pin. And all this function does is it sends a digital write, it sends the pin high, it waits 5 microseconds. Now I hate delay, but 5 microseconds is what, 5 millionths of a second or something. That's not going to mess my code up. That's the sort of delay I can cope with. Notice that is not the normal delay, that is delay microseconds. Then what, by the way, the original code by my friend, what's her name, Runaway Pancake, had a value of 20 in here. I reduced it down until I get the smallest stable value working. Again, because I don't like any kind of delay in my code. Then what it does is it writes that the clock pin high, and then we jump back to our main code again. And then what I've done is for Q equals 0, Q is smaller than the number of chips on the system. So now it's going to cycle through both chips. The first thing it does is it says, get me some data. And it passes the data pin and the clock pin. Now obviously it sends the data pin because it needs to know what pin it's going to receive the data on, and it sends the clock pin because within this function it manipulates the clock to do what it needs to do. And this is the bit that I sort of Runaway Pancakes sort of code. I messed it around a bit and altered it, but basically it works through the 8 registers and it pulls the data back until it has got its register content. The register content is the zeros and ones for each like register on the chip. Once it has all of the 8 bits of data, it does its little bit of stuff with the clock pin, and then it sends the data back to my main function. And when it sends that data back, I then put it into my buttons array, and then the function gets called again and it puts the data into the next element in the array. So that means at that point my function here, my array, now contains both sets of clock data, and 0 has the data from the chip closest to the Arduino. So if you like, as the more times you run this, the data is coming from further and further away. It's just squeezing itself down that sort of hose pipe of data, and it's taking it in 1 byte at a time. At this point, the code is finished. Everything below here is just displaying the data. But that is all you need to do to get all the data. Now you have a series of zeros and ones, and that's what I'm displaying here. So because of it's a binary thing, you can see that I've got a button is pressed on number 100. Unfortunately, it's 100 on both. Let me just alter that a sec, make it a bit more interesting. There we go. He says trying to get the pin in and it won't go in. Let's hope that sticks in there. Right, so now we've got 2 buttons connected on each board, and we can see the binary values coming through. And from that, a little bit of code that I did here, I did a bit read. So I now read through the array until I find a value that is a 1, and at that point I know which button has been pressed on each shift register. So I can see that on shift register 0, let's just stop this for a moment. So I can see on shift register 0, which is this first one, I've got a button pressed on pin 0, and I've got a button pressed on register 6, which obviously is this one here. Then on the second board, the second shift register, I've actually got something pressing on pin 2 and on pin 4. So at that point, whatever I need to do to process these buttons, that's about it. So it's a very, very simple function that works. I've no idea why the original shift in function didn't work in the Arduino example, but this code works really, really well. And by writing it in this simple form, it just means if you want to add endless chips onto your system, all you've got to do is change the value here, change that to 10, and instantly now this will work for 10 chips. It's as simple as that. So I hope that has been useful to you. It's a bit of a shortish video today, but it's something, believe it or not, I thought this was going to be a sort of a 20-minute job. It's taken me nearly 7 hours to work through all of this, but at the end of it I'm very, very happy with the function that I've written, and I will now install that into the ESP Now Rail project that I'm working on. So if that's been useful, please click the like and subscribe, and I'll see you in the next video. Bye for now.